Okay, now let's see deletion. We never discussed anything about the deletion for an AVL tree, right? The reason is because it's quite simple. Everything is just reversed. Deletion is only a kind of reverse of the insertions. So first of all, no matter what, we're going to have to delete one node from an ordinary binary search tree. So this is a quick review. That's why we do deletions in an ordinary binary search tree, right? The hardest part is to delete a degree 2 node. Then we can try to find either the largest node in its left subtree or the smallest one in its right subtree and replace this node by the node we selected. And then continue either recursively or iteratively to delete the replacing node from that subtree. And that node, if it's the largest in its left subtree or the smallest in its right subtree, it must be a node of degree no more than 1, right? If it's the largest, it must have no right subtree, or if it's the smallest, it will have no left subtree, right? So we just continue to delete a degree 1 node in the worst case. And to delete a degree 1 node is to replace this node by a single child. And eventually we're going to end up at deleting a leaf node and simply to reset its parent link to nil. But in the AVL tree, by deleting one leaf node, it might cause a subtree being unbalanced. So if it's unbalanced, we're going to have to make some rotation to rebalance the tree. But if we are not lucky, the rebalance of this subtree might make the height of this subtree getting smaller. And if the height of this tree gets smaller, it might cause the unbalance of a larger subtree. So we're going to have to make another rotation to rebalance that subtree. So in the worst case, we're going to have to start rebalancing from a leaf node and keep doing rotations from bottom up to keep rebalancing all the trees. So in the AVL tree deletion, in the worst case, the number of rotations we have to do is proportional to the height of the tree, which is log n. So that is the main advantage of red-black tree, because in a red-black tree, in the worst case, it takes only 3 rotations to have it done. So we're going to see. So in the red-black tree, when the degree 2 node is deleted, we replace this node by some other node and keep the color of this node. So the whole point is that we don't want to change the black height of this tree. As long as the number of black nodes is not changed, we don't have to reconstruct the tree at all. So whenever it's possible, do not change the color of the node. Okay, so just replace this node by some other node and let's keep the color. And to delete a degree 1 node, the same thing. Replace node by some other node and keep the color. We have to face the trouble only when we have to delete a leaf node, and if this leaf node is a black node. That is the only case that we have to do something to rebalance the tree. If we really have to delete a black node from the tree, what's going to happen to the rest of the tree? So there will be one path that its black height will be shorter than the black heights of other paths, right? And certainly we don't want to change every other path. To solve the problem, we must add one more black node to this path. So it's safe to simply delete this black node. Okay, so the whole point is that we must try everything to add one black node to the path of the replacing node. And this is a little bit complicated. We're going to have to handle several different cases. Case 1 is this. Suppose X is the node to be deleted, and it has a black parent plus a red sibling. Step 1 is to swap colors and rotate. Swap the colors of its sibling and its parent, and then make a rotation. But so far, nothing is really changed. The problem is not solved because before the rotation, we have 2 black nodes along this one and 1 black node along this path. And after the rotation, still we have 2 black nodes only along this path and 1 black node along that path. So the problem is not solved and we have to continue. An important fact is that after the rotation, its new parent must have another black child. Why? Why is it guaranteed to be black? Why is it impossible to be a red node? It's because this one, before the rotation, this one must be the left child of this W. And this W was a red node. If it's a red node, both of its children must be black. So after the rotation, its left child will become the right child of this new red node. Okay? And we realize that at this moment, the problem is still not solved. The difference is that after the rotation, we have turned the parent of X into a red node instead of a black node. And we can be sure that its sibling is a black node. Then we're going to have 3 different cases. What's in common is that the siblings of X are all black nodes. Okay, in case 2, both children of its sibling are black nodes. In case 3, its left child is red and right child is black. In case 4, we don't care about the color of its left child, but its right child is red. Now let's check them one by one. So in case 2, everything is black. Remember that the purpose of everything we do is that we would try to add 1 extra black node to this path. Okay, to solve case 2, the strategy is like this. Step 1, let's remove 1 black node from these 2 paths. Let's change the color of the sibling from black to red. Therefore, it's like we have removed 1 black node from these 2 paths. And then we're going to face 2 different cases. Case 1 is if the parent is red. If the parent is red, simple, we just color it to be black. It's like swapping the colors of these 2 nodes. And the problem is solved. Why? So let's check. Before we have 2 black nodes along these 2 paths, and after there are still 2 black nodes. And before we have only 1 black node here because this one is red, and after we have 2 black nodes along this path. So we have 1 extra black node along this path. Now it would be safe to simply cut this one, and the black height along this path would remain the same. So the problem is solved if its parent is red. And the more complicated case is if the parent is not red, if it's a black node. So everything is black here. So by changing the color of W, we have removed 1 black node from these 2 paths. And the number of black nodes along this path is not changed. Then what we must do next is we must continue to add 1 more black node to the path of X. We move X up. And this X is no longer this one, but this one. Let me explain it. It's like we keep a pointer pointing to the node and we define that node to be X in the sense that we would always try to add 1 extra black node to the path of X. In this case, we just move our X pointer up, pointing to its parent. And from now on, we're gonna try to add a black node to the path of this X. And if we can add an extra black node somewhere, then we can recover the number of black nodes for these two paths. And at meantime, there will be one extra black node along this path, and therefore it will be safe to cut this one. So in the worst case, we're going to have to keep moving up if everything is black along the way. So you just keep moving up. It takes log n time to move upwards, but there's no rotation involved. We're just changing colors. So we just keep moving up until we encounter one of these two cases, either case 3 or case 4. In case 3, the initial situation is this. It has a black sibling, and the left child of its sibling is red, and the other one is black. In this case, the strategy is again swap colors and rotate. Okay, swap the colors of these two nodes and make a rotation. Is the problem solved? Not yet. Okay, so let's continue to consider this W. W is always the sibling of X. Alright, and this is actually case 4, where case 4 means it has a black sibling, and no matter what its left child is, its right child is red. It's just like this. Its right child is red. And the solution to this case is, again, swap colors and rotate. Swap colors means to color both two nodes to be black nodes, and color this one to be whatever that color is. If this is red, this is going to be red. If this is black, it's still black. Okay, and then make a rotation. Let's rotate. Is the problem solved? Yes. Really? Now let's check. Say before we have something like this. This is a possible black node plus another black node along this path, right? And after we have this color plus a black node. So the black height is not changed. And along this path we have question mark plus a black plus whatever that is. And afterward we have question mark plus black plus whatever that is. So this path is okay. And before we have question mark plus one black node. After we have question mark plus two black nodes. That means we have finally successfully added one extra black node to this path. Now it's safe to simply cut this one. So put them all together, we can see that in the worst case, there are going to be at most 3 rotations. One rotation in case 1, and it's going to turn into case 2, and then case 3 to case 4. And there are totally 3 rotations involved. And the log n step is here, right? If we are not lucky, we're going to have to keep moving the x pointer upward till we reach the root. So that part is log n, but that log n only involves color changing, not rotations. Now to check whether or not you have really got the idea, let's have a test. Say this is the tree we have and you're supposed to delete x. What would you do? This is what? This is case 1. What is case 1? Case 1 is when it has a red sibling, right? And the solution is what? Swap colors and rotate, right? So swap colors and make a rotation. But the problem is not solved since before the rotation we have 3 black nodes. And now still we have 3 black nodes. So we cannot simply remove this one. And now this is the situation of case 2. It's actually 2.1, the simple case, where its sibling is black, but its parent is red. So what do? first change the color of its sibling into a red node. If the color of its parent is red, then we simply change the color and turn it black. And now we can cut this node. Okay, next, let's try to delete 17. Delete this one. So this is the case. This is actually the symmetric case of case 2.2, where its sibling is black and its parent is also black. So what do? Step 1, change the color of its sibling. Make it a red node. And step 2, move X upward. Now, this is the new X. We will try to add one extra black node to this path. Its sibling is black, and its sibling also has 2 black children. This is still case 2. And its parent is also black, so it's case 2.2. So what do? Change the color of its sibling and move X up. Now X becomes the root and has no sibling anymore. So we can stop the iteration and check. In this case, if X eventually becomes the root, it means that although we haven't added any extra black node along this path, but we have successfully removed one black node to every other path, and therefore it's now safe to cut this one. Okay, one more test. Let's try to remove 8. What can we do? Now in this case, the sibling is black and one child is red, and therefore that's case 3. It's actually the symmetric case of case 3. Okay, in case 3, what do? First, swap colors and rotate. Okay, swap colors and rotate. So after the rotation, the problem is not solved yet, and it turned into case 4, where the other child is red. Okay, so what do? Step 1, swap colors, and turn the colors of both nodes to be black, and color this one to be red. So swap colors like this, and then rotate. Therefore, we have one extra black node along this path. Now it's safe to cut this one. Okay, finally, as a conclusion, let's compare the AVL trees with red-black trees. They're both very good self-balancing trees. The difference is only the number of rotations involved during the insertions and deletions, especially the deletions. So it actually depends. If in some application, the most often used operation is find. If your user would ask you to find information frequently, then AVL tree is better, because the tree height of AVL tree is a little bit smaller than that of a red-black tree. Therefore, if we simply compare the search times, AVL tree is faster. But if there are a lot of insertions and deletions involved, then red-black tree runs a little bit faster. And that's probably the reason why it is more popularly used in implementing those library functions.